Thank you. The subject of this talk is cache side channel attacks as an example of how CPU design can become a security problem. About a year ago from now, I was preparing a talk about how to detect the rowhammer exploit. And one guy on Twitter tweeted that he could do it in JavaScript, which threw my plans to the wind. And I had to figure out how he did it, because I had to find out how I could detect that as well. And everything looked like it was going to be something to do with the cache. And so I started reading up on cache side channel attacks. And about 4 hours later, I wrote my first cache side channel attack. The interesting thing here was that I was actually running my rowhammer mitigation in the background, doing long-term testing of it. And it triggered. I detected my cache side channel attack as a rowhammer attack and was like, what's going on here? And that became the start of a year of researching what you can do with the caches in modern CPUs. And what you're about to hear is the results, some of the results that I've gotten in this year. So when I prepared for this talk, I was thinking about what is it that I want to bring across here. So I made an agenda for myself, and I decided to put it in a slide. And the first point that I want to make is that hardware design has security implications. What I mean by that is in fact, a lot more than just that statement. The first thing is, usually we think that if the software is written correctly, we will be safe. But that assumption breaks when the hardware does not do what we think it does. And the second thing is, when I wrote CPU design as a problem, I specifically chose the word design because this is not about bugs. This is about design decisions that are made by implementing the CPU. So that's the first thing I want to get across. The second thing I want to get across is that cache side channels are a real danger. I hope to show you that we can do lots of crazy stuff with cache side channel attacks, and that this is not just an academic study field, which it has mostly been until now. And I hope to get that across as well. The third point is that despite that these attacks are hardware enabled, we actually do have a chance to defend against them in software. So, moving on. Cache side channel attacks are attacks that are enabled by micro-architectural design of the CPU. What this means is that cache side channel attacks is not an attack on its own, it's a mythology. What is actually happening is that we can figure out how other software uses memory, and we can use that to infer secret information. What I mean by architectural design of the CPU is it is not a requirement that the cache is designed the way it is for the CPU to be part of the family. That is, there is no compatibility problems in changing the design. It's just plain design decision that could be done otherwise and hasn't. Cache side channel attacks are probably the most important side channel in modern computers because of the bandwidth that the memory subsystem holds, because of the size of modern caches that measures in megabytes, and the central position in the computer system. With the bandwidth, it's just a matter of how much data you can get across your side channel. The size makes it more stay longer and be able to actually get the data out of the side channel. And to understand the central position in a computer, I like to compare it to a side channel in the floating point unit. That could be a side channel in the floating point unit. The thing is, you can write a software without using the floating point unit. In fact, most software doesn't. But you cannot write a piece of software without using memory, and by extension, the cache subsystem. So this is why I think this is the most general kind of side channel attack there is in modern computers, and it's really, really dangerous. Because side channels are part of hardware design, they're notoriously difficult to defeat. I don't see any chances that Intel will be sending me a new CPU anytime soon, at least not without paying for it. And it is possible that this could be fixed in microcode. I actually don't think it can, but it's possible. Fact is that no vendor has defeated cache side channel attacks in microcode so far, and it's unlikely to happen, I think, because, say, Intel have been doing like 5 or 6 generations of CPUs without fixing this problem. So we are more or less forced to move into software mitigations for side channel attacks, and I hope to show that this is indeed possible. Who am I? My name is Fogh. I've been playing with malware since 1992, and you can reach me on Twitter or by email. And if you like to hear more about this stuff, I actually blog about it. You can get it there. So before I proceed, I should probably say that I will be using material made by other people. And at the end of my slides, which you can download after the talk, you can get the entire literature list and see what's mine and what's not mine. I don't want to take credit for whatever other people did. So you don't summarize a year's worth of research in an hour. So I'll restrict the scope here to talk about modern Intel CPUs, specifically Sandy Bridge through Skylake. Probably the next generation will be vulnerable to these attacks as well. This means i3s through Xeon is affected throughout. Most Celerons are, and some Atoms as well. I will mention AMD CPUs from time to time, just to point out the differences. You can do cached side channel attacks on AMD CPUs as well. They work differently than they do on Intel. Cached side channel attacks work on other CPUs as well. It's been demonstrated that you can do side channel attacks on ARM processors or on mobile devices as well. So there is many caches in modern computers. In the translation look-aside buffer system, there's caches. I have a paper coming out soon about abusing them for lots of funny stuff. There's a row buffer cache in the DRAM that you can use for side channel attacks. I have helped pioneer that side channel attack. And what we'll be talking about today is the data caches, what everybody thinks about when they hear CPU caches. That is the cache between the CPU and the main memory. We will be focusing on the shared L3 cache, and I hope you'll understand why when we get to it. So here I want to show that the L3 is, might be a microarchitectural thing, but it's not small at all. As you can see, the cache is rather large part of the real estate in the CPU. Another interesting thing that you can actually see in this die shot is that it looks like that below each core there is a specific unit for that core, and that is actually what is happening. These are called slices. We'll talk more about slices later. So to hammer home my point 2, that these things are really dangerous, I asked myself, why is this interesting? Well, cached side channel attacks do not respect privileges. They can be done cross-CPU, cross-core, cross-VM, cross-user, out of sandbox. If you get code execution, basically you can do a cached side channel attack. It's pretty much that simple. There can be many uses for cached side channel attacks. Covert channels, first that comes to mind. That is where a hacker has an implant on your virtual server and is sitting on another virtual server, is extracting data through the cache and not through the TCP IP, which of course means he cannot be detected by PCAP or deterred by firewalls and all this kind of stuff. I think that's mostly academic, but they do allow us to measure the speed of the side channel, and we can actually stream 720p HD video through the cache real time. So I think the point is that we have lots of bandwidth here. More important is stealing crypto keys. You don't actually need an implant. You don't actually need to be in the same trust domain as the key that is being used. You just need to be on the same processor. Well, not even that. You just need to be on the same computer to steal keys. It has been demonstrated that you can steal an RSA 2048-bit key on a live Amazon server. If you think that it's going to be better with elliptic curve cryptography, you'd be wrong. If you think that symmetric encryption is much better, well, AES has been broken as well. I should mention here, cached side channel attacks are attacks on implementation, not on algorithms. That means that RSA is not generally broken, but there are implementation of RSA which will leak the private key if you are on the same processor, same computer as an attacker. And remember, this can happen from inside a sandbox as well. So there's more mundane thing like spying on keyboard input, mouse cursor on the screen, and there's the really weird stuff which I have been involved with, is breaking the kernel RSLR, and you can actually do quite a nice kernel RSLR break with cache side channel attacks. So if you think this is a wide spectrum, it's because it is. It is because what we're doing is we're looking at how applications use memory, and every application uses memory, and it tends to leak information about what it is doing, and we can use this and abuse this with cache side channel attacks. So let's get technical. How the data cache works on Intel computers. Imagine that Core 2 does a memory request for memory. Well, it's first served in the L1 cache if it's possible. If it's not possible, it will be served from the L2 cache. And if it's not in the L2 cache, it will be served from the L3 cache. If it's not in the L3 cache, it will be checked if it's in the L3 slices on the other cores. And if it's not there either, it will be fetched from physical memory. What typically happens is that the physical memory is then written into L3, and if the L3 is already full, something will be thrown out. This is called eviction. The second thing we need to know about this cache is that this cache hierarchy is that it's a so-called inclusive cache hierarchy. That means that what data is in the L1 caches has to be in the L2. What's in L2 has to be in L3. With the L3 having this shared structure, meaning that if an attacker is able to put something into the L3 cache, it will be available on all cores. If attacker is able to remove something from the L3 cache, he will remove it from all cores and all caches from the entire hierarchy. And this allows him to manipulate the cache. We'll see how we can use that later. The last thing we need to see at the slide is what's not there. You don't see any rings, kernel privileges, user privileges. There's nothing like that. It's not because I'm lazy drawing this thing. It's just because it's not there. And that's what effectively enables us to do these things. To summarize it, the important cache features is almost any memory read-write is placed in the cache. The cache is a mirror image of memory activity on the computer. Second, L3 is shared globally across all users and privilege levels. And the final is inclusive cache hierarchy. If we remove memory from L3, we remove it from all caches, meaning we can manipulate the cache. So how is memory stored in L3? Intel's problem here is it takes a lot of infrastructure and time to keep track of the position of each byte of memory if it would be anywhere in the cache. So Intel have made two design decisions to solve this problem. And the first is it doesn't work on bytes. It works on cache lines. A cache line is typically 64 bytes of consecutive physical memory. The second design decision is, well, I should mention that of course, divides the problem by 64, which is by far not enough to solve it. So Intel has made the L3 cache an n-way set associative cache. What this means is that any cache line belongs to a cache set, and the cache set to which it belonged is determined by the address, meaning that from the address you can tell where in the cache a certain cache line is going to be. There are 2,048 cache sets per slice, meaning that on 2-core CPU it's before 1,096. Each set can store n, which is typically 12 or 20 cache lines, depending on the total cache size, meaning that when we request memory, we have to search 12 or 20 ways to find our cache line. Actually, it's not searching, but it's multiplexing, but it's the same thing, really. So we can look at this graphically. Here, you see down in the memory, I have given different addresses, different colors. And these colors have to match to the color of the cache set. That means that if something is green, it will be cached in set 1. If something is blue, it will be cached in set 2048. If something is red, it will be cached in slice 1 in set 1. Right? What we should also notice here is that Intel has chosen to distribute the cache lines over memory so that they are not in blocks, but they're spread out over the system. This design decision is so that applications that typically use memory rather in a local area will use multiple cache sets at once and thus have the ability to use more of the cache. So this is very good design for performance. The thing is, it allows an attacker to look into sets instead of working with the entire cache, which makes the problem for the attacker much more manageable. So here is an example code which we can attack. I hope there's no errors in there. That doesn't have to be. The function that I've written here is purely made up. It's inspired by the GDK library implementation of keyboard handling, and what it essentially does is turning keystrokes into Unicode jars. And here my simplified version. If it's uppercase, it uses a different function to turn it into Unicode than if it's lowercase. So you have these two functions, and in all likelihood, these will be placed on different cache lines and in different cache sets, which we saw before. And this means that we can effectually, if we could see into the cache, we would see that calling this function would place different material in the cache depending on whether your password uses an upper or lowercase letter. This is not a real thing. The real thing is much, much bigger and actually leaks a lot more data, but it doesn't fit on a slide. But I will use this example to explain the cache side channel attacks in a moment. So if you try to remember uppercase and lowercase, different cache sets, different cache lines. So common for all cache side channel attacks is that we can determine if something is in the cache. How this works is if we access it, the cached version will be much faster, typically around 80 clock cycles. The uncached going to main memory will cost around 200 clock cycles. So we actually have a pretty big difference between how long it takes to access memory. I told you before, we can manipulate the cache. This typically happens in one of three ways. The first is eviction. This works by accessing memory in a cache set until everything that was previously in there has been replaced with attacker addresses. Then there is a flush. Intel has decided to give us an unprivileged instruction, the CL flush instruction, which we can use to evict individual cache lines from the entire cache hierarchy. And finally, there's prime. Prime works pretty much like evict, except now we access memory in a pattern so that the attacker afterwards knows which addresses are in the cache at a given point in time. So I like to think of cache attacks as there's three big cache attacks, and then there's tons of variation of these three. There are other cache attacks. I will not be talking about them. They all work in the same way. The attacker manipulates the cache to a known state, and then he waits for the victim activity, and then he examines what has changed. As you see, the big three, evict and time, prime and probe, flush and load. The primitives for manipulating the cache is the first part of it. The second part is how we actually see what's in the cache. So evict and time works in this way. We execute a function, and it'll set up the cache so that the next time you call this function, it'll go fast. And then we time the same function and use this as a baseline. Then we evict a cache set that we think is interesting, and we time the function again. So if step 2 was faster than step 4, the function probably used an address congruent to the cache set in 3, meaning in our password case, which is a bit unrealistic because you can't type a password in such a function that wouldn't work, but if you could, we would know if the user has used an uppercase letter or not in his password. So it's a bit of a problem using this function. It limits the attack. So there is a more powerful attack that alleviates this problem. It's prime and probe. The first step of prime and probe is manipulate the cache to a known state, that is, to make sure that a cache set contains only known attacker addresses. Secondly, we just wait for victim activity, and finally we time accessing addresses used in step 1. What happens is, if the victim used something congruent to this set, he will throw out one of our addresses, and we'll get a cache miss when we try to attack it, and we'll know he used memory congruent to this cache set. This has an advantage because we can just repeat the attack, run it over and over again, and we'll not only, if we do it on both cache lines in the example function, we'll not only get if he's using lower uppercases, but we'll actually get how many chars it's using, we'll get upper and lower case, and where they are in the password. Since the GDK function actually leaks a lot more data than that, that basically means that we can reduce the entropy of your password if you type it in a Linux or whatever box that uses the GDK library quite significantly by a cache side channel attack. Flush and reload works similarly to prime and probe, but instead of priming the cache, we flush an address that we know to be interesting. This address has to be shared in shared memory. Then again, we wait for victim activity, we reload, and we time access to the shared address. If the timing is fast in 3, well, it was placed in the cache by the victim. So basically, same deal as prime and probe for the rest, and we'll move on to comparing them. So victim time, the accuracy you get is cache set congruence, and we require a function call. This has an advantage. We don't have to synchronize with the client. We know from calling and ending the function when the client is running, when the victim is running. A downside is that this is post-mortem analysis. We only get what actually happened during the function call, not what happens inside of it. We don't get any spatial, temporal resolution out of that. I have used the victim time to break kernel KSLR. I ended up doing a modified version because it was faster, but it actually, you can use this attack to break kernel mode KSLR. Prime and probe, again, accuracy is cache set congruence. We do live analysis this time. We get the entire password. And the scary thing about this is it works well in JavaScript. Why is this important? Well, this is important because browsers use JavaScript, and this means that cache side channel attacks becomes a remote executable, a remote exploit. Finally, flush and reload. The accuracy is on cache line accuracy. We get this accuracy because we share memory with the victim. Again, it's live analysis, and there's another advantage of this attack. That is, it's faster than the prime and probe. Faster means that you get better temporal resolution when you're spying, meaning that if you're spying on a crypto algorithm and want to get real nitty-gritty data, you're better served with flush and reload than prime and probe. Flush and reload doesn't work in JavaScript. Well, it actually does, but it's not like it's very useful. So I had let this point stand in my slides. Shared memory is unfortunately not as rare as one would think. There are shared libraries. Think of kernel 32 DLL in Windows. The code of it is mapped into all processes in the system and distributed to each of the processes through the paging system. So it's just physical memory mapped into others. This is enough for us to do cache side channel attacks on. This actually happened to every library you load on Windows, so there's plenty of shared memory. It's not just Windows that does this, it's most operating systems, standard procedure. Then there's another feature. This is called deduplication. This is where the kernel or hypervisor searches for identical pages in physical memory. If it finds one, it frees one of them and uses the paging system to provide for the client's needs throughout the system. This works even on virtual machines. My personal opinion is this should not be used on any system for any reason. It's just a security nightmare. It basically not only allows you to do flush and reload attacks. If it was only that, it would be bad. But there's deduplication attacks. You can speculate on doing row hammer across VM through deduplication. A recent Dutch paper, I think I read it Monday, used deduplication to get an info leak in the Edge browser and row hammer its way out of the sandbox. So you shouldn't be using deduplication. If you are, well, all bets are off, I think. Cache side channel attacks are not as perfect as one would like. They're inherently noisy, and the reason is there is other code than the victim running on the computer. Well, that's one of the reasons. So if that code uses the same cache lines, it'll disturb prime and probe and the victim time. If it uses the same cache set, it will disturb that. Another thing is these are essentially timing attacks, and there are other shared subsystems in the CPU, and other uses of these subsystems will change the timing of the information. This is not particularly important for the basic cast side channel attacks because the time difference of 120 clock cycles is pretty substantial. We'll take a look at another cast side channel attack in a moment, a variation of flush and reload, where the timing difference is much smaller, where it becomes a real issue. Then you have interrupts from hardware and whatnot, which disturb you. And finally, you have the hardware prefetcher. Both attacker and victim and unrelated code can trigger the hardware prefetcher to load cache lines into memory. And this, of course, will cause false positives in the cast side channel attack. Except for the hardware prefetcher problem, the solution is repeat the attack and rely on the law of large numbers. Of course, you cannot ask a user to enter his password 10,000 times, but you can expect that on a web server, your key will be used a couple of thousand times, so we could get results. So moving on to where a lot of my work lies is detecting cast side channels. I'll be using flush and reload as an example of how to do it. The method actually does work for other cast side channels as well. First, we have to need to know something about performance counters. Performance counters are built into the CPU. We have 18 performance counters on modern Intels that we can program to count micro events. There's a lot of micro events that we can count, including instructions decoded, interrupts received, and of importance to us, L3 cache misses and L3 cache references. Also, you can optionally get an interrupt when the counter overflows, and we can actually set the counter as well, which allows us to get an interrupt on any instruction that causes these events. This has two effects. That is that we can use this to keep track of how many caches arrives in a particular time segment, and we can get an interrupt frame and actually analyze instructions that causes these events. We'll use both these methods to detect different kinds of side channel attacks in a moment. On a side note here, we can use performance counters to look for security-related weirdness. It's not just cast side channel attacks. You can look for rootkits, you can look for rowhammer, for return objective programming, and stuff like that. Flush and reload here, it is in sudo assembler code. First, we manipulate the cache to a known state with a clflush instruction. Then we wait for the victim. I should probably make a comment here on the wait. Say you're trying to spy on a keyboard, there'd be no reason to be fast about it. You could wait a few milliseconds, and nobody actually types that fast. If you're spying on crypto, you probably don't want to wait at all. You want to be as fast as you can be while repeating this attack. So what essentially is happening is you're in a race condition with the victim. You're running on different cores, and you always want to be before the cache is cleared. So don't wait. Then the rest of it is just timing accessing the shared address. I do this here with a mov instruction. It could be any instruction that accesses memory. The mfins instruction is because the CPU is capable of reorganizing memory requests, and the mfins prevent that. The attack actually works without it, but it works better with it. And the rest is just using the RDT&C instruction to get time, and depending on how long it took, you calculate the information you want. So how do we detect this? Well, the mov register shared address, when the victim did not use the shared address, we get a cache miss here. In fact, if the victim uses the shared address that we just flushed, we'll get a cache miss there. The thing about cache misses is that they're rare in real applications. And we can use this to detect it with performance counters. My original suggestion was to just interrupt every number of cache misses and look at how long it took and just have a value. If it was too short, well, we have a cache side channel attack. And that worked pretty well on most cache side channel attacks. Since then, other researchers have improved it. Some have put the performance counter data into machine learning and found that that works pretty well. Others have just compensated for general activity in a memory subsystem by using a proxy, say, CAF's references or something like that. And this makes it a bit better with less false positives and less false negatives, mainly because that when you have high activity in a memory subsystem, you get CAS misses as a result that are benign. But in general, this works pretty well. So if you're wondering about the story I told you in the beginning about rowhammer, if you look at this and remove everything that has to do with timing and do this on 2 addresses, you get this. And that is, in fact, the original code for the original rowhammer paper. Rowhammer was flush and reload. It's no coincidence that my rowhammer detection detected my flush and reload attack. For those of you interested in rowhammer, the rowhammer JS that I was trying to detect replaced the CL flush instructions here, which are not available in JavaScript, with evict routines that work just by accessing memory in a patent, which of course is possible in JavaScript. So what often happens when you come up with a good mitigation is that somebody comes along and figures out how to bypass it. And this time it's no different. I actually had the idea before, so when I was approached by Daniel Gross and Maurice Clementine about how we would go about detecting a side channel attack that doesn't cause as much CAS misses, I immediately said, oh, you're timing CL flush. And that gave me the opportunity to actually review the paper on flush and flush. So the basic idea about it is that flushing an address from the cache is slower when the address you're flushing is actually in the cache. The logic behind this is obviously that the instruction can shortcut and doesn't have to do as much work as when there's actually something in the cache. So here you have sudo assembly code for the flush and flush attack. And the only thing that's changed is that the mov instruction has been replaced by CL flush. The authors of the article called this a stealth side channel attack, and we can speculate about the reason. And the reason is flush and flush does not have a reload phase. And that means there's no mov, no shared address, meaning we get no cache misses, meaning that the detection method that I originally proposed is not going to work very well. So we can ask if performance counters are useless. The answer is no, we can actually do something with them, but I can just see that I have enough time to go off subject. The flush and flush is advantageous in many ways over the flush and reload. The thing is, first thing we should notice is that the CL flush instruction is much faster than accessing memory because it doesn't have to access memory. That means it's just about twice as fast as accessing memory. This gives flush and flush better temporal resolution when you do it in attacks. The second thing is the CL flush instruction itself will actually return the cache to a known state, meaning that if you repeat this attack, you don't have to go back to the first CL flush instruction, you can go right to the wait phase. This makes it faster again, and this gives it a lot better temporal resolution and much more bandwidth as a side channel. In fact, the flush and flush attack is the attack which had the covert side channel which can stream video in HD. Another thing about flush and flush that's advantageous, explained earlier that the hardware prefetcher sometimes gives problems. And one of the good things is that the CL flush instruction does not trigger the hardware prefetcher. So that's a nice feature of it. It can be that the victim still triggers the hardware prefetcher, so the problem is not solved, but it's less relevant. So returning to the subject, detecting flush and flush. The core idea about detecting flush and flush is that it always has a certain structure. It's a CL flush instruction bracketed by high-resolution timers, the RDTSC instruction in short sequence. And we can ask ourselves if we can detect this, and the reality of it is that we can. So before that we can go on to actually detecting flush and flush, we'll need to know some things about how we do it. And first, I should mention that this detection does not work on cross-VM with deduplication-enabled systems. It could mitigate the problem a tiny bit so that the attacker on the other VM couldn't use kernel mode, has to use kernel mode to do the attack, but he could do that. I don't think this is a big problem because I think you should turn off deduplication and that solves the issue. So things that we use to carry out this attack is that the RDTSC instruction can become privileged if we set a flag in the CR4 register, the TSD flag. This will cause an access violation to be generated every time that the RDTSC instruction is used. We will use this to get notification of RDTSCs, and what we'll do is we'll use the access violation handler to emulate the RDTSC so that we will not interfere with benign clients. Also, we need to look at, we need to talk about that attacker cannot spend much time between the RDTSC, and that is because on multi-core CPUs, there's lots of things going on, and this adds noise to the channel. There is significance to difference to flush and reload here. The thing is, flush and reload, you have 120 cycles of difference in timing. With flush and flush, it's much faster. The difference is much smaller. It's just a handful of clock cycles. And there's a fair bit of noise, so the attacker is not capable of waiting too long before calling his next RDTSC instruction to end the timing of the attack. The final thing that we need to know about this is that when a CL flush instruction actually flushes an address in the cache, a performance event is generated, and it's a performance cache reference event. Unlike cache misses, cache reference events are quite frequent. Again, this is a testimony to how well the L3 cache actually works performance-wise, but we can actually use this for building a detection. So, I have designed this detection to be a two-stage attack, a two-stage detection. I have two reasons for doing this. The first reason is that the second stage is expensive performance-wise, and thus we want to avoid doing it on benign subjects, benign applications. The second reason is that this two-stage detection method is pretty flexible in terms of other microarchitectural attacks that do instruction timing. And I have this weird feeling that we're going to see more attacks of this nature in the next coming year, so I'd like to be prepared to detect these as well. What we do in the first stage is that we try to detect the bracket of RDTSC instructions, and here we use the CR4 TSD flag to get an access violation and count how many times do we see RDTSC instructions less than 2 microseconds apart. The 2 microseconds is a tuning value. 2 microseconds is pretty conservative to what an attacker can actually afford to spend between RDTSC instructions. If we get more than 2 occurrences of that in 2 seconds, well, we should proceed to stage 2, which is detecting the CL flush instruction. If we do not, we just do it again to make sure that nobody is starting a new CL flush attack. So, stage 2. So here we again use the CR4 TSD flag to get an interrupt on RDTSC. If we get this interrupt within half a second of being in stage 2, we know that it was not flush and flush, and we can safely return to stage 1. However, if it was less than that, we proceed to set up performance counting on interrupt references. Now, when we do get a reference get an interrupt on the reference event, we will use this interrupt. We'll ask ourselves, did we spend more than 2 microseconds since the last RDTSC? And if we did, we know that this particular RDTSC instruction is not part of a CL flush attack, or it's the end of a CL flush attack. So we'll return to the first part of the stage 2 and do the next RDTSC instruction. If, however, it was fast enough after the RDTSC instruction, well, we'll use the interrupt stack frame to find out where in memory the instruction that caused the cache reference was placed, and we'll read memory there to check if it's a CL flush instruction. Obviously, if it was a CL flush instruction, we will assume that this is a flush and flush attack. And that is a pretty fair assumption given that RDTSC instructions are rare and CL flush instructions are really, really rare. In fact, so rare I have not found a benign program that actually uses one, but that's another thing. If it's not caused by a CL flush instruction, we could assume that the attacker has put in a cache reference event to lead me astray to obfuscate his attack. And that's the reason that we go back to setting up the performance counters to get an interrupt on the next cache reference event. And then we just repeat from there. So, are there any problems with doing this? Well, causing interrupt penalizes performance on benign programs using RDTSC. And programs using RDTSC is actually fairly rare. There are some. Visual Studio, so it's fun programming stuff like this when your Visual Studio always crashes. Search Index or stuff like that uses RDTSC, but it's fairly rare. So we're not causing too much disturbance in that direction. But there is another possibly worse problem with doing this. Since we're spending time handling our interrupt and emulating the RDTSC instruction, we actually make the timer less accurate. For mitigating cache side channel attacks, that's actually a huge advantage, but it might not be for benign applications, which are also affected. So we should be aware of that. Then there is the question of, is there any other timers than RDTSC? And if there is, how will that impact the detection? Well, that's pretty easy. The entire detection hinges on the RDTSC instruction being detected. Somebody suggested that I could have a thread running, and in this thread, there's just counts up an address until another thread tells it to terminate. I've been playing with this. I've been unable in any way to show that this actually is fast enough or accurate enough in any way to do flush and flush with it. I'll be happy to be shown otherwise. I don't think it's happening. There are other kernel mode timers, including performance counters and stuff like that, or RDTSC could be leaked from kernel mode, and that, of course, will break my detection as well. Finally, there is a big problem with implementation. I implemented under Windows, and you run into this funny thing called patch guard that prevents me from hooking interrupts. My solution was actually using Windows XP for my implementation. My generalized testing, I have not seen too much performance cost of this. It's about a percentage, but it's very, very, very much across platforms. The thing is, I have not seen a benign program that actually makes it to the second stage. I've just not seen it. It doesn't happen, but CL Flush does it every time. And when you finish something like this, you always ask yourself, can you do better? And I actually think we can, and this will be part of my research for the next year, and I hope to blog on it sometime during this year. Maybe it won't work, so maybe you won't see anything, but maybe it will. So doing a talk like this, you actually have to omit a lot of stuff. And I left out all the gory details, and that was intentional because we don't really have time for it. Things I left out was things like how does the processor decide what to evict when we access other memory, called the eviction policy. How do we determine to which cache set a cache line is congruent? These are things that we can all do. It's all relatively recent research that shows us how we can do it. In the past, it has been done by another side channel attack, timing attack on figuring out when something gets thrown out of buffers, things like that. And I should mention there's other mitigation from cache side channel attacks beside mine. This is as opposed to detection. I'm actually not aware of any other method for detecting cache side channel attacks other than the ones I've talked about today. There is a feature in modern Xeon computers called CAT. I believe it's short for cache allocation technology. It's a performance enhancing feature, but it can be used for actually providing privileges for the cache. It doesn't work very well in my opinion, and this is why I more or less chose to ignore it while I developed this stuff. Another thing you can do is you can write branch-free cache set aware code. Now, what we saw in the example was that the feature that allowed us to spot what was going on in memory was that we branched. And you can imagine things like arrays and stuff like that being spyable. And if you make your code really, really careful, you can actually make sure that you don't leak any vital information by being aware of what cache set you're using and why, and avoiding branches and stuff like that. It turns out it's pretty difficult to actually do this. A recent example was that the OpenSSL library hardened their RSA implementation to be branch-free cache set aware. And as it turns out, somebody figured out a different cache side channel attack which broke the new implementation. This was called cache bleed. It's not like we cannot foil that as well, but it's quite difficult, and I don't think it's a method for the broad things. It's not like we're going to have a kernel that's branch-free cache set aware at any point in time. It's just too expensive and too difficult to write. It's not like we're going to see application developers handling your password in any kind of way, branch-free cache set aware. So it's great for crypto, but it's not going to solve the problem. So I've about reached the end of my presentation. I hope that you have all taken to heart that CPU design, we're talking about CPU design here, that it actually poses a danger to bug-free software. I hope you have all taken to heart that cache side channel attacks are actually quite dangerous critters and quite powerful. And finally, I hope that you have a general idea that we can do something about this in software, and we can even do something about this in software when the attacker is adapting. So my closing remark will be that Sophie D'Antoine is going to make a closing keynote, and she will be touching this kind of stuff. You can be sure that you'll find me there. I hope to see the rest of you guys as well. If you have questions, don't hesitate to ask. I actually love talking about this stuff. It's a hobby of mine. I don't do this professionally. It's a hobby. This means that if you have questions in connection with this talk, please ask them. If you want to talk in private, please get a hold of me. If you want to email me, do so. Thank you.
Okay, thank you for the talk. I'm sure we all learned a lot about it. Does anybody have any questions?
Hi, cheers. I was just wondering what was the roll hammer detection that you were running that you mentioned at the start on your own machine?
The roll hammer detection basically is the same as the flush and reload detection I talked about here. It basically uses a performance counter to count cache misses, and if you get too many in too short a period, well, it's not benign software, it's going to be row hammer. It turns out it could also be flush and reload, but either way, it's not benign. It just doesn't happen on compute. Well, it can happen, but it's really rare, and so for most people, it's going to be good enough, but there are false positives in things like lib quantum, like weird stuff that accesses memory in weird patterns a lot of the time. So, hope that answers your question.
Well, how much of having shared memory is a requirement to the attack?
Shared memory is required for flush and reload and variations thereof, which includes flush and flush. The thing is, the reload phase, you access memory to find out the state of the cache after the victim has run. For prime and probe and evict and evict in time, we are using cache congruency, which is a lower criteria. That means that you actually don't have to share access to memory, meaning that you can do cross-VM attacks, whatever you really like. You don't need to know anything about addresses that is not your own to actually do this. So prime and probe for cloud things, it's probably the one to go to, where evict in time is probably more of the special use cases.
Yeah, the answer. Are we talking here about physically tagged cache lines or virtually tagged cache lines? I'm not sure about the Intel architecture.
Can you talk a bit louder?
Yep. Are we talking about physically tagged cache lines or virtually? I'm not sure how it works on the Intel architecture. I know on other stuff. But the cache lines that you have are physical address memory, right?
When I talk about addresses, I talk about physical addresses.
Okay.
It's all about physical addresses. The L3 and L2 caches are both driven by physical addresses, which allows us to bypass the paging system. The L1 cache is a bit special in that direction. So running attacks on the L1 cache is an entirely different story.
Doesn't this pose a requirement that you know actually the physical address of the data that you want to attack?
Well, it's one of the things that I omitted. What you typically do to find out cache congruency isn't the physical address. If you're using large 2 megabyte pages, the virtual address actually leaks enough information to do it. But what you do in cases is that you do a timing attack on cache congruency. So by loading, say, n different addresses and then timing how long it takes to access them, adding one address, timing all 11. At some point you'll find out, oh, I created a cache miss, and you'll know that you have, within this set of data, you'll have a set that is congruent, right?
Okay, thanks. Awesome talk.
Okay, any other questions? Okay, it appears we are done then. Thanks a lot again for the talk.
Okay, thank you.